My name is Dave Kolas. I work with BBN Technologies, I guess now Raytheon BBN Technologies. Most of our semantic web group is in Arlington, Virginia, but I've had the privilege of coming up here to talk to you guys today. I'm going to give a brief overview of the type of semantic web work that we have done and are doing at BBN. And then I'm going to go into a little bit more depth in two tools, semantic web tools that we have built and are currently using, a triple store and a federated data system. So an overview of the type of semantic web work that we do. We were actually the prime contractor for the DARPA contract that developed the DAML language and got a lot of this technology off the ground. My colleague Mike Dean worked on both the OWL and Swirl specifications. We're currently doing some work with Vulkan going forward in new KR languages, and I'm actually currently participating in the OGC effort for developing GeoSparkle, which would be an effort to have a standard. New language isn't right because it doesn't extend Sparkle in any way. It's a standard Sparkle, but having standard vocabulary within Sparkle for functions and properties for doing geospatial indexing and processing. We also build applications for customers both in the DoD and Intel community. I guess in reference to Marco's bar graph at the beginning, we have deployed systems with RDF, so that's good news. This is sort of a graph of some of the major projects that we've done, and this starts with the DAML program and expands out to more research DARPA work, and also more applied work with NGA, with other Intel community customers, and delving a little bit into the commercial. With that, I will start first with our triple store. And our triple store Parliament has been around for quite a while. It was originally called DAML when it was developed during the DAML program, and there was no such thing as finished OWL yet. But we're trying to talk about it even more now because we've recently released it as an open source project. So it is available at SemWeb Central. All of the source code is there. Please, we love you to go and take a look and play with it. In the last couple of years, we added spatial and temporal indexing to Parliament. So this means that all of your great spatial and temporal data sets you can add in there and then do the type of queries that you would expect to do with a spatial, say, relational database, except that you have the advantage of RDFS inferencing and an RDF query, Sparkle query as well. If we take a look at the architecture of this, it's implemented as a persistence layer for Jenna, as are, of course, many other triple store backends. We have an intermediate layer of Jenna's graph implementation that splits queries amongst the spatial temporal indices and the direct triple store Parliament underneath. We're working a little bit to better integrate with Arc right now so that we can do more high-level query optimization. And that's work that will probably be rolled into the project here very soon. We do use an external spatial index using PostGIS for keeping that. We didn't have time to implement do our own R-tree implementation. We didn't necessarily think there was a reason to do so. So it depends on those libraries and depends on Berkeley DB for the temporal indexing. I'm going to go into a little bit more detail now that this is open source about how the internals of Parliament's main triple store indexes statements, because it is somewhat unique compared to the strategies taken by some of the other triple store implementations. And this is, of course, all the brainchild of Mike Dean when he was flying on a plane back and forth at some point years ago. Parliament focuses on having balanced performance between queries and insertion, as opposed to some of the other research triple stores that have, or some of the more recent triple store research that has come out is focused on very fast query times for like data sets. Like many triple stores, the main body of the data is separated into a resource dictionary and a statement table. And the statement table is really the key creative insight to how this part of Parliament works. You have the standard subject, predicate, and object in your statement row. And then from that, you have pointers to the next statement in the list that shares the same predicate, the next statement in the list that shares the same subject, and the next statement in the list that shares the same object. So what you get is this triply linked list of statements that runs all the way through the triple store. There are some bit field flags for encoding statement attributes, for deletion, and whether or not a statement was inferred, whatnot, but that's a little bit low level for this. The resource dictionary works much like the resource dictionary for lots of triple stores. You've got a bidirectional mapping between numerical IDs and URIs and literal values as necessary there. So looking at an example here of a built-up small Parliament store here. On the left you have a resource table, and this has pointers to the first statement in the statement list that uses a subject, or the first statement in the statement list that uses a given predicate or object. And it also has count values for how many statements each of these, in each position, that particular resource shows up. So if we look at resource 3 there in the list, we can see that it first appears as a subject in statement 5 at the bottom there, and the links work upwards. And first appears as an object in statement 1, and you have the counts there. What this means for insertion is that all you're doing is pushing another statement onto the bottom of the list there and updating these counts and the first pointers there. So this means that we have very good insertion performance compared to other triple stores. In terms of query performance, you have a potentially really ugly worst case in certain situations. We have the counts there to guide you to which statements in your triple pattern are best to go to first, which are the most selective. It turns out that the worst case performance doesn't really affect us very much, and this chart is here to explain why that is the case. This has the list lengths for Parliament for a bunch of common linked data sets here. You have the size in millions of triples there, And then for each subject, predicate, object, you have the average and standard deviation of the number of statements that these appear. So you can see in the middle that the length of the predicate list scales with the size of the data set. So as you would expect, you have to skip through quite a bit of predicates when you're matching on predicate. But the size of the subject and object lists actually stays quite small, even for these very large data sets. So we have basically an average of around 5 elements in the chain for any given subject, and 5 or so elements in chain for any given object. So if I am looking for a triple pattern and it has a fixed subject or fixed object in it, I can very, very, very rapidly get to the few relevant statements that are in the KB with just a small number of hops. We've done studies that compare Parliament to other triple stores, and a strength is insertion performance. Another strength is query optimization for complex graph patterns. I can send references to anyone who is interested in these. We're very interested in doing further work on query optimization with Parliament. In our deployed systems experience, we've had to do systems where basic graph patterns in Sparkle queries are 50 triples long or 60 triples long. And none of the current Sparkle benchmarks really address this particular use case. So we're trying to do our best to delve into what it means to really do a good job of optimizing triple pattern order in a complex query like that. And we're working more on Parliament's internal rule engine and optimizations to the storage structure. And with respect to the spatial indexing, as the GeoSparkle spec becomes mature, we're going to evolve our system to make use of that, of course. With that, I'm going to change gears to a piece of software called SEO Scalp, and I'm going to be able to save a little time in explaining this because it's going to overlap somewhat with the previous presentation. So some of the motivations are quite the same. We have underlying data in a bunch of different formats, relational databases, web services. In an ideal world, there are lots of Sparkle endpoints that are sitting on the web that we'd like to integrate. And we know, as was described before, that just trying to jam all of that data in one place is not a good solution to the problem. And further, we want different sets of users to be able to look at the data from different perspectives. So we don't want to just recreate one new schema to rule them all, but rather provide different vocabularies for access to the same set of underlying data sources. And obviously, we're going to use semantic web technology to link these data sources. This is an overall architecture diagram for Scalp. We have an end user application up at the top. They feed Sparkle queries into the federation component, which is semantic query decomposition, or squid to be cute. Down at the bottom, we have semantic bridges, and these things interact with other types of data sources in a way that works well with the federated. Again, we have domain ontologies at the top. There could be multiple of these within the system. So if you have different groups of users that are working in different different domains, they can still have different translations of the same underlying data. The way we link the federator to the data source ontologies is via Swirl rules. And I'll talk a little bit more about how the detail of that works later. So as this Sparkle query comes in, the first thing that has to happen is this federation engine needs to look at all of the Squirrel rules that it has linking the domain ontology to the data source ontologies and do its query rewriting. And this is sort of the main interesting part of how this works, so I'll talk more about it in just a moment. It's to generate the subqueries and then start the data access process. And this is sort of a back and forth type thing as it builds the answer graph at the top from multiple sources. So it may need to go to some of the sources more than once as it connects these pieces of data together, because if you have a query that crosses multiple data sources, the part that needs to go to one data source may be very selective. And if you go to that data source first, you may get back a key that allows you to go to a second data source with a much more selective query and thus not deal with a much larger set of data. So the system is designed to be able to feed keys that are given back from one query into subqueries for the next source. And so as it does this, it's starting to build a result graph, and as the result sets from these subqueries come back, it begins spooling the result set to the overarching domain query and giving answers back to the client application.
So that's asynchronous. You get that back in the state generally.
It's actually synchronous, so it works in the very same way as like a JDBC result set that you're used to. So you may ask your query and get back, as you start iterating through the list, it's going to do a batch of X number of results and give those to you. And then as you ask for the next one, it's going to start spooling those subqueries to get you that next batch of data. That's actually one of the things that we worked on most recently. In the first version, it sort of aggregated all of the data into an internal inference model and then answered the query back from it. And that was very problematic for all the reasons that you would think it was problematic, because if you asked a query that had a whole lot of answers, tell me all of the people in this database who were born in this time range, then that internal model got really, really big and took forever. So that's been eliminated now, and it works significantly better. In that internal rule expansion stage, you have the incoming Sparkle query, and what happens is it walks through the Sparkle algebra and looks at all of the triples that are in the query. And for each triple that's in there, it needs to check its available set of Swirl rules and see which of these rules from the data source can infer this particular triple that's in the query. And so it begins to expand out all of the possible ways to infer the triples in the query from the data sources with variable unification. And so what it's doing is creating a much bigger Sparkle query with a bunch of potential unions in it that as the different data can be inferred from a bunch of different data sources.
And that's entirely how rules are handled. The rules are completely handled by query writer.
Yes. Yeah. So obviously that puts there's some like limitations that are the result of that, which are the ones that you would expect. But the practical trade-off has been worth it so far. Once you have that big expanded query, you can use the ontology information that you have available to really prune it back down, and this is an efficiency thing, especially. Disjointness allows you to eliminate a lot of possibilities, a lot of possible clauses from your expanded rewritten query. If you know that two data source ontology classes are disjoint, and you know that one of them is required by a different part of the query, you can trim out the ones that are not compatible with that. Subclass, subproperty reasoning works it's also via rule rewriting. And another big help here is functional and inverse functional properties. You can use functional and inverse functional property information to infer that two variables that were generated by a different part of the query expansion must be the same variable, and thus reduce the complexity of the generated subqueries that you're doing. So one of the things that we really wanted to stress here is that we separated an independent domain ontology, and we want you to be able to write that completely independent of how the underlying data sources are represented. And that's why we have Swirl as the mapping between the sources and the upper things, because that gives us a level of expressivity in doing this this mapping that is different than at least the other approaches that I'm familiar with. Some practical things that come up when trying to link an RDF data representation to relational databases. One is sometimes you have to create new entities on the fly. If you have a relational database and it has the address information of a person merged right into the row of the person. So person, their street address, blah, blah, blah. Ideally, in our domain ontology, we don't want to be tied to that particular decision. So we create a Swirl built-in that allows you to create a new entity in the mapping process for just the address. And then you can have a two-hop thing in your actual domain ontology. So obviously, this is outside the typical Swirl expressivity. You're not allowed to create new objects ahead of rules, but it's really a necessity in terms of doing what we want to do here. And again, in order to keep that expanded query small and concise, you have to do Scalp reasoning with this to eliminate some of the extra variables there. Another one, in a relational database, it's typically it's a closed world model, so the lack of a row in a database can mean something in your domain ontology. So we just have to have a way to support that. So we use another Swirl built-in to negate things in the domain ontology, and then as the Sparkle queries are generated, that happens with the standard optional and not bound combination of operators to actually execute queries. A quick note on performance. I unfortunately don't have a good front-end demo to show you today. This is essentially mostly back-end software. Pre-processing of the query does not take very long at all, especially considering that without this, otherwise you're potentially merging data sets in your head. The streaming results is what I referred to earlier. You start to get answers back as soon as some answers have come back from all of the subqueries. So your client application is free to page through them as is appropriate for the UI. And it's, in general, putting very little overhead over just executing queries. The one area that probably still needs some serious work is some advanced algorithms to better decide what's a good query ordering for the subqueries that are being produced. Oh, and nobody, in the top right corner of all of these slides, that should say Raytheon BBN technology. So please don't call it. And that was all.